Okay.
Okay, and could you tell us your name and your role in the project?
Sure. Thank you. Sorry about that.
That's all right.
I'm Sang Han, professor in the Department of Chemical and Nuclear Engineering. And maybe I'll give you a short version of what my research group does over the next few minutes. And so here's...
What is your role in the Septet project?
Oh, Septet project. So the project itself has to do with harvesting energy in urban settings. So it could be radio frequency signals that are out there. In addition to, of course, the obvious, which includes sunlight, heat, energy, and whatnot. But specifically, this project is focusing on harvesting energy from a variety of different sources that are available in urban settings. So in my case, our group is focusing on harvesting energy from the infrared spectrum. So
what interests you about the project in general, or the specific area that you're?
I think our society has progressed to such an extent that we're using a lot of mobile devices, and whether they're mobile devices or even computers or other devices that communicate, they typically communicate with using infrared. So probably the most common example is when you use the remote control to turn on and off your TV. That's exactly infrared signal. So there are many stray signals that are out there, and I think we can harvest even these communication signals and whatever is out there available in urban settings. We're trying to harvest that and turn it into a useful energy. So
that's so interesting. So
yeah.
I thought that the infrared was about harvesting heat energy, but it's not. It's actually about infrared that we're putting out into the environment.
So yeah, in addition to the heat, there is a lot of infrared signal that we're using for mobile devices and computers. When the computers communicate with your printer in a wireless setting, it's all infrared communication.
And is there a
short range, but yeah.
Okay. And is there more energy to be gained from that type of infrared? What is the? Is there? Is it a very large source of energy? Do you know?
Oh, I don't think so.
Okay.
But you're right. You have a very good point. There are many. These are probably not very strong sources of energy. But just to provide you with an example that there are many of these out there, especially in urban settings, and we're trying to see whether we can harvest energy from these variety of different sources.
So you would say that it's more of a kind of tactical source of energy on the fly while you're traveling, or
yes.
Okay, cool.
Yeah.
So why don't you tell me about what you wanted to talk about with your group and the specifics?
So I'll give you sort of a broad overview of what we do, and then specifically focus on the project that we're working on for the Septet program. Okay, so I don't know if you can capture that, but so let's start from this left-hand corner. Our group does a lot of thin film processing. So these are traditionally used in electronic devices, microchips and whatnot.
Let's hold on a second.
Yeah.
Sang should give you this PowerPoint.
Yeah,
so
and just take it from the PowerPoint.
Yeah, and that'll look much better than focusing on the screen.
Yeah,
so
yeah,
why don't we get a lot of good stuff of him, the Head and Shoulders, and then we'll get that later and be able to reference it. I mean, I think as long as you can sort of see which slide he's on, then you know which one to. Does that work for you?
Yeah,
and
it
turns out that during editing, if my diction doesn't sound very clear, please just.
Definitely.
Oh, well.
Plenty will be cut.
Yeah, I mean we've got Tito and we've got accents like mad everywhere. So. It's been the transcribing. Jared's been doing some of the transcribing. Plus technical, terms and stuff, of course. So, but yeah, don't worry about it.
Okay, so we do thin films, and so in this case, what you're looking at is a very porous film, and if you're building transistors today, whether it's the latest Pentium chip or the Pentium chip, Intel chips that are from, I'm sorry, Pentium is dated.
Okay.
They're a latest chip that contains on the order of billion or more transistors on a very small block. But they're all built on at the bottom of the silicon stack. That is, it's two-dimensional. Most people think that just because they have billions of transistors that are stacked in three-dimensional space, but that's not true. They're all two-dimensional. And imagine having these small transistors, and then you need to connect them, interconnect them, right? So there are multiple levels of metallization that is crisscrossing, connecting these different transistors.
Can I ask you a dumb question?
Yeah.
What is a transistor?
Transistor is a switch. Essentially, it's a switch that you can turn on and off using an electrical potential.
So these are movable. Well, no, I guess they're solid state
Solid
within
state,
the
yes.
material.
Yeah.
Okay.
And so then when you have these multiple metal lines, they tend to crosstalk. And to minimize that, you want to use a dielectric film, insulating film, that has a very low dielectric constant. And so porous film tends to provide you that property. So that's one of the things that we explored some time ago. But by and large, we do fabrication, whether it's at the nanoscale or microscale. So we carve out very small features, as you can tell here, very thin film, and in this particular case, we are carving out circular features that are very uniform, and it assumes a square lattice pattern in this case, as you can tell.
What is the difference between the microscale and the nanoscale?
Simply, nanoscale is a little smaller, another 3 orders of magnitude smaller.
Is there a big difference in the fabrication process?
Yes, it becomes a lot more difficult when you go to nanoscale, especially top-down, what most people would call a top-down approach, where you're using lithographical steps. So you use a thin film, whether it's a polymer or a dielectric film, and then you carve out very small features using lithography. And defining these small features requires typically electron beam exposure, and that can be a very expensive step. So it's not an easy thing to do. So we do deposit thin films, study their material properties, we carve out small features in the thin films, and we also use these templates to grow high quality films or quantum structures. So the figure that you're looking at here is a top view of germanium quantum dots grown on top of silicon surface. So it's a top view, and each pyramidally shaped structure is about definitely less than 100 angstroms by 100 angstroms. Very small features. As you can tell, they're randomly distributed on the surface. But ideally, if we can actually have them grow in a uniform pattern, that can lend itself to a wide variety of different applications. And so we had used a templated approach, and recently we're using, I don't know if I have a slide to show you today, but today we're utilizing what we call stress transfer. So what's the best way to describe this? So in this case we're using an alloyed surface. It's a mixture of silicon and germanium, and we use a template, two-dimensional template. When I say template, this is a template with pillars that are coming out. Maybe I'll show you the image later on. And when you press it down onto the silicon germanium alloyed surface, the press region, under the press region, germanium, which is a bigger atom than silicon atom, they tend to migrate out of that region. Whereas the silicon would remain in that region. And so if you press it down and anneal the substrate, what happens is that you can introduce a compositional variation in a two-dimensional pattern. And then we can subsequently use that pattern to grow these quantum structures at precise locations.
So does this, when you talk about these three-dimensional shapes and these pyramids, to go back to what you were saying about the transistors, this allows transistors to be located in a three-dimensional? Because you were saying that
Oh,
it's
okay.
two-dimensional
Yeah,
only,
so,
and is that
yeah,
the
so,
idea?
so that, I mean,
One
the
idea?
conventional transistors are built on a flat substrate, and you introduce impurities. When I say impurities, this could be it could be boron, phosphorus, and whatnot. And then transistors actually are built into the substrate. Maybe I should go. Okay, maybe that's not entirely true anymore today. So now they're actually going 3D. When I say 3D, the transistors now use the actual channel region where the electrons and holes, the charge carriers, transport through. Now they're using what people call fin structures. So these are very narrow silicon, for example, that is carved out, and metal lines actually surround these fin structures, and so they're called FinFETs.
You should close this door.
Yeah. So transistors can be made three-dimensionally today. Still sitting on a two-dimensional substrate, but it's three-dimensional in terms of actual shape. Here, the quantum dot cases, we are thinking maybe someday we can use these dot structures to build single electron transistors.
Wow.
Yeah. So that's what.
Wow.
Yeah. So so it's sort of looking further into the future and see what we can do. Now, so not only do we grow thin films, fabricate or carve out small features, we grow small quantum dots and quantum structures. It's a fancy way of saying that when you say quantum structures, it has to do with confining the electrons or holes within, literally spatially confining it within a structure. And here, this is a top view image. So you can imagine, in fact, this is a magnified view of this surface. And you're looking at these white circular structures that are rather serpentine structures that you're seeing. Each bright circle is actually 2 germanium atoms. They are atoms. We're looking at atoms, literally looking at atoms.
Wow. Are you getting him, or are you getting the screen?
Oh, I have both.
Oh, okay, good.
Yeah,
Are you getting? You're not getting the camera reflected, are you? It's a very reflective
no,
surface.
No,
okay, good.
Yeah, totally good.
So, and we actually dynamically look at how they move around over time, and these serpentine structures actually wiggle, and we look at the energetics, what sort of energy it takes to actually assume a kink position versus straight position, and so we look at the energetics of these serpentine structures, which turned out to be a precursor to forming these quantum dot structures, it turns out. So conventional thought was that before forming these quantum dots, individual atoms on the surface will move around, diffuse around, and they form a dimer, and the next atom will come over and form a trimer, and they continue to gather to form a quantum dot structure. But it turns out that there are other intermediate species that fill the gap. So counter to what people have thought in the past, there are other stable intermediate species before forming these quantum dots.
You know, I don't want to move things too far away from what the goals of the project are, or the simple goals in terms of energy harvesting, but it begs the question of, and I think that we have been skirting around this issue as well with all the information about the solar decathlon building that we have been visualizing, where you were getting a lot of information, and I wonder, like, is what you're working towards also something that is used for information transfer as well as energy transfer, or could be, because you had mentioned chips and transistors, and I'm just curious if what...
I mean, certainly they are components of communication devices. Is that what you're asking?
I guess, yeah. I mean, are we looking at like the next generation of, Intel microcomputer,
So I mean, these are some of the technologies that can potentially contribute to the next generation of microchips. and which will operate at a much faster speed and high-performing devices. So
That might power themselves.
so you can't really have free lunch. You definitely need energy to run these devices, but if you can harvest them from wasted energy that's readily available in urban settings, then I think that's a plus. So.
Nice.
So now, some time ago, well over 10 years now, we started using the fabrication technology to carve out very small channels into the silicon substrate. So what you're seeing here is a cross-sectional view of these slit-like channels that are carved out, rather carved into the silicon substrate, and we put a lid on top to seal the channels. And it turns out that we can manipulate the electrical potential on the walls of these channels locally. So if, imagine these channels running in and out of the plane, very long. When I say long, longer than it is wide. So when I say long, it's only about a centimeter or much shorter than a centimeter. But then these channels are about 100 nanometers wide, so you can imagine how small they are. And we can actually use the channels to separate biological molecules. And also we had done some solution synthesis of quantum dots. Instead of using the substrate to grow these quantum dots, we also used the solution synthesis using inorganic precursors, chemicals, to form very small spherical quantum dots. And we also functionalize a lot of these silicon or germanium or other semiconductor surfaces with organic functional groups. So these could be long sort of alkyl chain molecules with different termini. So one terminus may have carboxylic group. The other terminus may have, the opposite terminus may have an amine group. And we can potentially, we did in fact, we had shown that we can functionalize these semiconductor surfaces with the functional groups, and then we can continue to build from there.
What is the potential purpose of, I shouldn't put my finger in there, what is the potential purpose of separating out biological molecules?
Okay, so we'll get there. So then, studying things at a small scale, looking at some fundamental surface chemistry, that's all fine and dandy, but ultimately I think showing working devices is a true demonstration of your scientific and technological understanding. So we actually build 3-5 multi-junction cells that are fabricated on top of these engineered substrates, for example. We actually build fast transistors and characterize them. And we also separate these biological molecules. So what you're seeing here is a horizontal line, for example. It's a dark strip that's about 180 microns wide. And because human eyes cannot distinguish anything smaller than the wavelength of visual light, and so 100 nanometer wide channels that are running horizontally, of 180 of them, you cannot distinguish them. It's below the diffraction limit. And so what we had shown here is that we can bring in a mixture of proteins, but we can separate them and concentrate them by a factor of 100, 1,000, 10,000, and whatnot. So the reason why we're separating different proteins, for example, let's imagine, so this is a topic that I never discussed with the group, septet group. So I have been collaborating with Dr. Robin Oles in our medical school. She does research in neonatal care, including sepsis, hypoxia, and whatnot. And certainly neonatal sepsis is one of the leading causes of infant mortality for low birth weight infants. Then ideally what you really desire is being able to predictively diagnose sepsis for a low birth weight infant before serious clinical symptoms show up. And because they have such a small blood volume, if you can actually analyze their blood from a heel stick microliter volume blood, that would be ideal. So the idea is that from a very small blood volume, you place this little drop of blood into